In this video, I'm going to talk about Euler's equation and how to solve Euler's equation. This is what an Euler's equation looks like. It's ax square y double prime plus bx y prime plus cy is equal to 0. And here a, b, and c are real constants, okay, real constants with a not equal to 0. Euler's equation is actually a special case of general equation called Cauchy-Euler equation, which is this: a sub n x to the power n times nth derivative of y plus a sub n minus 1 times x to the power n minus 1, then n minus 1th derivative of y, and you keep going down all the way, and the last term is a sub 0 y is equal, and all of that equal to 0. Again, the conditions are the same. A sub I set constants with a sub n not equal to 0. The easy way to remember this thing is this. Look at the derivative, the order of derivative y. You take the derivative n times, so you have to multiply it by x to the power n. You take derivative on y n minus 1 times, so you multiply it by x to the power n minus 1. So that's how the progression goes. So if you follow this structure, then it is easy for you to kind of remember this thing. Now, Euler's equation is the special case where your n is equal to 2, right? N is equal to 2, then you get the Euler's equation. Now, let me go ahead and solve this equation, or try to solve this equation. So, ax square y double prime plus bx y prime plus cy is equal to 0. We have seen equations of these types before. However, those were homogeneous constant coefficient second order differential equations, okay? You didn't have x square or the x terms in the first or the second term there. And those ones we kind of tried out this way. Our solution was y of t is equal to e to the power rt of that format. But here, the solution will actually be slightly different. So let's use y of x instead of y of t, because we use the variable x here. We are going to try out something like y of x equal to x to the power r, where r is a constant, okay, and x is, of course, the variable. Now, if we do that, so if we take this solution and assume it to be our solution to this differential equation, we can go ahead and substitute this value by taking the derivatives. So this is what we are going to get if we do that. Note that the first derivative of this is going to be y prime, which is going to be r times x to the power r minus 1. And obviously the second derivative, y double prime, is going to be r times r minus 1 times x to the power r minus 2. And if I plug these values, this and these values into this equation, I'm going to get something like this. Obviously, this x to the power r is not equal to 0. So that means my other term has to be equal to 0, which is going to give me ar square minus ar plus br plus c is equal to 0. And this is nothing but a quadratic equation in R, and you can solve it. Now, there will be three scenarios that you'll be dealing with. So the first scenario is going to be this. So case 1, where the roots are distinct. So that means R1 is not equal to R2. And in that case, the solution is pretty straightforward. Your solutions are going to be x to the power r1 and x to the power r2, right? So your solutions are x to the power r1 and x to the power r2. So your general solution is going to be y of x is equal to c1 times x to the power r1 plus c2 times x to the power r2. Very straightforward and easy case. Case number 2, which will be when R1 is equal to R2. That means roots repeat themselves. So let's call this R. Both of them are equal to R. So my solution, one solution is going to be y1, or y1 of x is equal to x to the power R. Now, how do we go about finding the second solution since the roots repeat here? We are going to pretty much do the same kind of trick that we have done in the past. So let's call my second solution, let's call it y or y2, doesn't matter. And it's going to give you x to the power r plus some function u of x, okay? Now, our job is to determine what is u of x. Now, if we assume that this is our actual solution to this differential equation, to the given differential equation, then, by the way, we could take the first and second derivative and plug it into the differential equation and then simplify it by using the reduction of order method, and then we can simplify it. Upon simplification, you will find the following. So your u of x, you will see ultimately is going to become nothing but ln of x, ln of absolute value of x. Now, this may come with some constant c1 or something like that, c2. But don't worry about that for now. You will see as you do the work, it will be obvious that your y2, let's call this y2. So your y2 is going to be of the format x to the power r times ln of absolute value of x. Now, the actual process of deriving the value of value of u of x, by the way, you will learn about it when you actually solve a problem, and it's a pretty straightforward process that you have done in the past. Okay, you'll be able to substitute these values, and you should get the value of u of x. So when it's done with an example with concrete numbers, it will start to make sense. But just keep in mind that if one of the solutions is x to the power r, and the other one is going to be x to the power r times ln of absolute value of x. So your general solution or the closed form solution would be here c1 x to the power r plus c2 x to the power r times ln of absolute value of x. The next case, or the third case, is the complex case. So case 3 is going to be a situation where your roots are going to be complex conjugates, okay? So r1 and r2 are complex conjugates. So it's going to be r1 is equal to, let's call it maybe alpha plus I beta. And r2 is going to be the complex conjugate, which is going to be alpha minus I beta. Now, in this case, you kind of want to remember, so one of your solutions is technically going to be, let's call it y1 is going to be x to the power r1, right? Which is going to be x to the power alpha plus I beta. And the other one is going to be y2 is x to the power r2, which is going to be x to the power alpha minus I beta. Now, this is something we can simplify, this one and this one. So let's go ahead and simplify this. Let's do it for alpha plus I beta. So x to the power alpha plus I beta, I can simplify it to x to the power alpha times x to the power I beta. Now, I'm going to take the x to the power I beta and simplify it, then plug it in right here. So x to the power I beta, I could write it as e to the power ln of x to the power I times beta. Remember, ln and exponential functions, they are inverses of each other, right? So they cancel each other out. So if you have something like x, you could write it as ln e to the power x, or you could write it as e to the power ln of absolute value of x, okay? Because ln and exponential are inverse functions of each other, so they cancel each other's action. Now, let's go ahead and take it a little further. E to the power ln x, I need to put absolute value here, okay? E to the power ln absolute value of x I beta, which I could simplify further to e to the power I beta times ln absolute value of x. All right. Now, you probably do remember that e to the power I theta is equal to cosine of theta plus I sine of theta. Using this formula, I could simplify this, and that is going to give me cosine of beta, let's put a parenthesis here, beta times ln of absolute value of x plus I times sine of beta times ln of absolute value of x. Now, this is the same as just this thing, x to the power I beta. Okay, so now I'm just gonna go ahead and plug in this into the original expression, x to the power alpha plus I beta, and then simplify it. If I do that, I get the following. So this is what I get. As you can see, my y1 is equal to x to the power alpha plus I beta. I break it down into 2x to the power alpha, x to the power I beta, and then I plug in this and simplify it. It's pretty straightforward. X to the power alpha cosine of beta ln absolute value of x plus I, x to the power alpha sine of beta ln absolute value of x. Just by looking at this thing, you can obviously see this is y1 and y2 is going to be just same thing, except that it's going to be minus sign here. Here is going to be minus. So now by looking at this, you can see that your actually solutions to this differential equation, or to this particular case where roots are complex, are going to be, so one of the solutions is going to be, let's say y1 of x is going to be, don't be confused by this y1 and this y1, okay? I could use some other notation too. So y1 of x is going to be x to the power alpha cosine of beta ln of absolute value of x. So that is one of the solutions, okay, fundamental solutions. And the other one is going to be y2 of x is going to be equal to x to the power alpha sine of beta times ln of absolute value of x. So your general solution is going to be y of x is equal to c1 y1, which is this value, plus c2 y2. If I write it out, this is what I'm going to get. And that is going to be the general solution for the third case, case number 3, where the roots are complex. This is how you'd solve an Euler's equation. I hope that this discussion was helpful. Thank you very much.